Okay, here we go. Sorry about that. A little bit late here. Hi, I'm Dusty. Welcome back to my lab. Today we're going to do our weekly live lab. Last week's, I was supposed to upload, broadcast, stream, whatever you want to call it, and, uh-oh. Okay, there we go. You hear me now. Okay, that totally just derailed me. Anyway. Welcome. Last week I thought that I did a 2-hour live stream and I actually didn't hit go live on my software, so that didn't happen. Honestly, it was probably for the best because I was kind of bumbling around in this software that is very similar to what I know, but not the exact same thing. Anyway, now I've already got a good idea of what I want to do, and we're going to do a combination. We're going to show the actual computer-aided design process, and then also simulate it in simulate it in the real world. Simulate in the sense of it isn't going to be the final product. It's just going to be a test run. So we're going to do that with some prototyping techniques using a breadboard here. We're working with 12 and 5 volts because we need the microcontroller to control the fan. I'm gonna have to remember and catch you guys up on what the plan is here, because I'm still in the mindset of, oh yeah, I already talked about this for 2 hours, but I really didn't. So first things first are probably going to be that Bean's going to want to jump on me, and then I do need to replace the battery in this multimeter quickly. And sorry I was late. I was looking for a USB-C cable. I think we should be in pretty good shape here now. I paid $15 for the software for my phone. So here, check this out. This is pretty cool. Oh, whoops. Okay, so watch. Now it should actually be able to focus on this, I think. Maybe not. Okay, I know what it is. Only do it if... I really don't understand camera technology that well. Okay, see, there you go. So now you'll actually be able to see the boards up close and see what I'm doing and what I'm working with here. Okay. So I actually don't have a universal power supply, and I know that that's really dumb and kind of pathetic at this point, but I've used batteries and then little buck converters / transformers, whatever you want to call them, however they're configured at the particular time. So we're going to use a battery. Sorry, Bean. How does this work again? Okay, let me see if I can get this in the shot too. Let's see. Cool, cool. Alright. If you don't know anything about multimeters, I guess I'll zoom out too so you can get since we don't have to actually look at anything specific. If you don't know anything about multimeters, yours might be a little bit different, but it's less confusing and scary than you think. And ironically enough, the fancier, nicer multimeters are actually kind of more user friendly than some of the older style ones or simpler, cheaper ones. So the cheaper versus better version, the real difference is what's called auto ranging. So I'm not even sure. I guess this can probably go up to an insane 600 volts. I'm not sure. It probably can. This is a more expensive multimeter. But if you have an older version, which I actually ironically enough have laying here on the ground because I was trying to rob a battery out of it earlier, you'll see that this symbol here, the wavy one, that means that it's AC, so alternating current, and this is direct current. So if you don't know anything about that, basically what's running in your walls is alternating current and what comes from the power plant, and that's how you can transfer electricity far distances. DC is what basically all of your componentry and like things that you actually touch and work with, all your electronics actually run on. Just dropped a potentiometer. So right now, we have a fan that is a 12-volt fan. And how would you know that if you didn't know? Usually there's something written on it. This one, actually, I ripped the sticker off of, I think. Does this one have it? Yeah, this is the same fan. This one has the sticker on it. And usually you'll see some version of 12 or 24, some combination, like some multiple of 12. Why that is, I'm not sure. There's probably some weird just coincidence that occurred. So you'll see commonly 12 volt, 24 volt. Then usually there's a big gap as far as like what's common all the way up to 120 volts. So that's kind of what's nominal here in the States, and 240 is what's nominal everywhere else. So that's still a multiple of 12 and double 120. So 12 volts is real common. That's what your car runs on. That's what your car system runs on. Yeah, so super common. I have a 12 volt power supply that I also use pretty frequently, but we're not going to use that for this just because it's really bulky and kind of overkill. And I'll show you how the battery might sag in its voltage a little bit over time as we use it. So let's just continue here. What I think I'm going to do instead of the logo animation for the second half of the show is I think I'm actually going to design a little fume extractor, because you might be able to hear the white noise in the background of the shot, and that's because I have a fan blowing at the back of my head, which is usually what I do when I'm soldering, if I do anything. I'm in a pretty like open basement, so it's not like I'm in a super confined area. But one thing that I can do and what I want to do is I started working on this for a temperature and humidity controlled terrarium, and this is a HEPA gas mask filter, and then a 24 volt fan. So there you go. That's an example of the multiple of 12 rule. I'm pretty sure I tried this, and this will run at 12 volts. I don't know. It really should be the case that you can run a 24 volt fan at 12 volts, and it'll just run at a slower speed. And I think that's what's going on with this, and it seems to be fine. If you're concerned or like not exactly sure, I mean, I think I can imagine that there would be a weird scenario where that would not be okay. Just see how hot it gets. See if the fan starts getting hot. So, like, monitor it for a while, you know, and also like don't try to, you know, mess with it and give it voltages that aren't nominal unless you're willing to part with it, meaning it smokes and blows up. Probably wouldn't blow up, but it would get hot and smoke, and bad things would happen. It would no longer work. So just keep that in mind. Yeah, basically everything that you touch works on direct current. So that's what DC stands for. I don't know if I said that. So AC, it means that the current is going back and forth, and then direct current means that it moves in one direction. And it you know, depending on, you know, if you want to do like logical calculations, it kind of makes sense that there's like, in the same way that you would think of a flow chart, that's honestly kind of how logic calculations are done with electricity. And in order to do that, you need to have a flow in a direction, and not just, you know, not go back and forth, because you won't make progress if you want to think of it that way. I'm sure that you can do logic with AC, but it complicates things. So generally, like whenever you're doing computations or logic, which most electronics that you touch and interact with do, then there's a DC component. So a lot of times, in order to accomplish that, you know, everything plugs into a wall, which is 120 AC, which is a really high, relatively speaking, voltage AC current, which isn't what you want in order to do actual work. If you want to think of it that way, logically speaking, you can do work in terms of motors. That's usually how AC is directly implemented. But you have to convert it, so you have to transform it, and then I'm not an electrician or an electrical engineer. I mostly think about this stuff when I have to program and to build stuff. And I'm probably going to mess up all the terminology. So I won't even go much further than that. If you want to look into it, I have other videos where I am a little bit more careful about what I say and give some analogies. But yeah. So these are called wire nuts. And they come in lots of different sizes. And the way that they work is that there's just a little spring, a conical spring. Bean just jumped up behind me. And basically the idea is you just take the bare end of your wire, which is usually stranded, but not always, doesn't have to be, and you twist this spring onto it. You tighten it onto it, and it basically just, because it's conical especially, it gets nice and tight and grabs the wire. And then if it's the right size and it's the right tightness on there and whatnot, then you won't be able to pull it off, at least easily. So it's safety, and also an easy connection. This is what's used in a lot of your walls. So there's different versions of these, but like in your house's walls, this is actually what they use to combine the 120 volt wiring together. And some things to think about and consider when you're let me see if I can get this to work. Yeah, I'm having a hard time. It's like so small. Oh yeah, maybe I can do this. Yeah, there you go. Okay, so let me expand this a bit. So what'll happen and what'll get really irritating over time is, if you can see it, the strands, and the more strands and like the more finely stranded the wire is, the worse this will be. They'll get twisted into a really tight spiral, and then basically the spring will not be able to grab anything, and it'll just it won't work as well. Basically, it'll pull off a lot easier, and it's just more dangerous. So in order to fix that, you want to just turn it in the opposite direction. You know, kind of like splay them out a little bit more, straighten them out. And you can only do this so much before they'll start fraying really badly, and the little strands will break off and whatnot. So just like monitor your wire ends, because the thing about a wire is that it's really only as good as the weakest part of it, meaning like the smallest diameter part of it. If there's a bad connection anywhere on the wire, then it can potentially get hot, depending on what kind of current it's carrying. It's designed and spec'd, tested, to work a certain way. You can think about it with the water analogy and just imagine like trying to push way too much water through a pipe, and it's hard to imagine a pipe exploding, but what happens is that instead of exploding, the wire just gets really hot. Alright, Bean, are you trying to help? Okay, so what I want to do is I'm going to probe this voltage. You want to be careful whenever you're dealing with this. I'm gonna clamp one of the wires in my helping hands here. Some things that you need to have when you're working with electronics in general. I mean, honestly, if you want to do most things, you want to have a soldering iron. And if you have a soldering iron, then you want all the soldering equipment. So something that I didn't understand for the longest amount of time is that, like, you can get away with soldering certain things for a while without having flux or a sponge or a copper wick or a desoldering tool, and depending on what you're doing, you'll get away with that. But and also depending on the cheapness slash expensiveness of your soldering iron, the tip will get, it'll be good or bad, basically. And what I found is that I don't understand the physics of it that well, but basically if you don't have this stuff, if you don't have some form of flux, you can't actually wick any solder into your tip or into your part. So this flux, this is key. And like, you don't need anything really fancy. I mean, I don't know if I'm gonna get banned off of YouTube now for showing this. This is how it usually comes. It comes in a syringe for like PCB and more fine stuff, as far as like just smaller things. And whereas this like tub, this could even be used for soldering a pipe. So that's the thing. Flux is really just meant to allow solder to be absorbed into the metal lattice, I believe. And if it's not there, then it like the molten metal can't flow, including into the tip of the soldering iron. So over time, so this has been sitting here, and you'll see it's pretty dull. Don't want to burn myself showing you this. Put it in the flux, scrape it up a little bit on your rough surface, and then all of a sudden it's shiny again. Yeah. All right, babe, don't burn yourself on this. And so, like, but if you don't have the flux, you really can't. You're not going anywhere. Like you can't save it or whereas it really is just as simple as adding some flux to it, and then it immediately fixes the problem. So just keep that in mind. You'll be pulling your hair out, not understanding what you're doing wrong, and that's what it is. So Bean's driving me nuts here, but whatever. Here, you can say hi to him. So 11.31. That's slightly lower than what its nominal voltage is supposed to be, and that's totally within a reasonable range. And we can use it for a while, but keep that in mind. 11.31. We don't want to overdo it. And usually, how they do this now, that this is just some random blower fan from China, but usually what they do is black is on the outside. That's going to be your ground / negative. Red is your power, your DC plus. And then I don't really remember which one is which here, as far as which one they made the tachometer and which one they made the PWM. Honestly, don't know. So we're going to have to figure that out. Ways that you can do that. I think we can probe it and see. We might be able to see it even on the multimeter, the waveform like coming off of the tachometer. So the tachometer is basically just a signal that's generated that correlates and is the result of the speed of the fan spinning. And the idea behind that is you can then send the speed signal that correlates to the feedback that you're getting. So even if you send a 50% duty cycle, if you wanted to that to actually correlate with 50% of the total fan speed, so the highest fan speed, then you need to actually calibrate that to the tachometer. Generally speaking, it won't scale perfectly linearly. All right, you gotta move. Okay, so here's the easiest way to do this. Something that I want to do, we're going to use this microcontroller. It's a Arduino Jiao, and in the last stream that I tried to do, I talked about the different versions of this. So there's 3 different versions. This is actually an older version. It doesn't have Bluetooth or Wi-Fi capability, but at least for a prototype, this will be fine. And really the idea and what I want to do is I want to make a PC, a custom gaming PC / I mean, it could be used for a lot of things. This thing could cool a lot of things, including like a server rack, anything. You'll hopefully by the end of this series, whatever you want to call it, by the end of this build, you'll be able to understand and see the similarities and parallels between all the different control fields and just endeavors. Like it's all kind of the same thing. If you're trying to control a fan, no matter what scenario it's in, it's going to have these basic parts, at least nowadays. It used to be done a little bit differently. But what I want to do is, because there's kind of like a dead spot or an empty space in the market from my perspective, and kind of by design, you can buy water cooling / LED controllers for PCs. And I mean, certain motherboards, especially like the larger motherboards, come with inputs and like fancy controls for all that stuff stock. The problem is that different manufacturers will want to pigeonhole you into their proprietary setup, and the thing is that they're all basically doing the same thing. Like I just said, but what they'll do is they'll change the connector size and shape and make it seem like, oh, we have to do it this way because it's better or this or that, and frankly that's not true. So I mean, all you're doing is simple stuff. You're controlling a pump, which is basically a fan. It's controlled the same way, it's interacted with the same way, and fans and LEDs, and so it's something that almost any microcontroller can handle. It also is going to have to take in a temperature and modulate the fan speed off of that. That's the idea behind this as well. So one thing that's a motivation for me is that I have a smaller form factor motherboard, and oftentimes the smaller form factor motherboards don't have very many or not at all the right types of fan connectors or temperature inputs. So mine, for instance, especially the original motherboard that I had, didn't have a temperature input at all. So basically, you would have to modulate your fan speed / pump speed off of things like your CPU temperature or your GPU temperature. But the thing is that when you have a combined loop, when you have your CPU and your GPU on the same water loop, you really want to modulate your fan speed and pump speed, if at all, off of the water temperature, because that's what's actually relevant. If the water temperature starts to get warm, then you want to worry. But like a spike in your CPU temperature really quickly because you just loaded something is not a reason to increase the pump speed or the fan speed in your loop, because there's such a lag, right? So like, whereas that makes a little bit more sense when you have a CPU air cooler right on the CPU, and the CPU spikes up real quick, and then you want to dissipate that heat real quick, so you blast of air. Okay, that's fine. But like when you have it into a water loop that's all combined into one, you have all of that thermal mass of the coolant. So everything is like way delayed as far as, okay, there's a spike in the CPU, a little bit of heat is dumped into the water, but that hardly affects the average temperature of the water at all. So what I want to do is, and other people have done it and are planning on doing it in different ways. What kind of inspired me to revisit it is a post on Reddit that I saw where the guy's basically doing the same thing that I'm doing. I'm going to do it a little bit more accessibly, where I'm going to use like a pre-packaged microcontroller, whereas he was like basically doing like an electrical engineering job where he's taking the actual system on a chip, the actual brain of this, and then engineering a board around it, whereas I'm going to just engineer a board around this itself, which it's just his method is a little bit more pure and efficient, and like, whereas mine is kind of taking a prototyping tool and then making it into a usable thing, like or something that's buildable. They're kind of like just in different realms. Like he would have to build, like he would have to put together a kit, whereas I'm gonna possibly offer this PCB that I design, and then you buy all the other components, and then whatever. So have my USB-C here. This is how we're gonna plug in the Xiao to program it. Haven't downloaded my I guess we're gonna program this in Arduino IDE. I haven't programmed in a long time, so we'll see how that goes. Maybe we'll try to download Copilot. I don't know if you have to pay for that. If you don't know about that, Copilot is basically AI programming. So you it's like autofill, which is kind of what the AI ChatGPT is. I mean, it's just a really, really good autofill. It's like when you keep pressing like the next suggested word, except hooked to a gigantic neural network. But basically, like you start to type your code or import some code, and then Copilot goes, "Oh, here I'm analyzing your code in real time," and then we're like it'll give suggestions of which direction you want to take it, and apparently it's really good. And I mean, I only have heard that from one veteran programmer I was watching on the Lex Fridman podcast. I don't even remember his name right now. Really cool stuff. Anyway, okay, so I've had this soldering iron sitting here hot for how long now? Like a half an hour. So let's actually solder something just for fun, since that's always fun. Where'd I put my little prongies? Uh-oh. Probably knocked on the ground by Bean. Okay. I got more. 1 second. Okay, that's just because I didn't break it to the right size. All right, let me get my headphones on here. Okay. So you can see here, this is kind of the idea. Now, if you try to shove it on there, shove these prongs through these little holes, which this is also surface mountable, which is really cool. You can see the footprint actually here behind here. This footprint, you can actually solder this directly onto those pads, and that's how this is actually supposed to work. Or you can solder the pins onto a female header. So I don't know. I think I'm going to use the footprint and plan to solder this directly on. But for now, I'm just going to dedicate this as a prototype unit. So this isn't very complicated. You can get some irritating results. Actually, I'm going to use this as like a tool to autofocus this thing. Just do yourself a favor, grab pliers and actually use pliers or your micro snips and snip it to the right size rather than trying to do it with your fingers, because you'll break them to the wrong length and then you're just screwing yourself. So that probably wasn't smart. I just shot that to Timbuktu. There you go. Okay, so that's the right length. This time I'm actually going to count how many I need. How many are there on here? 7. So I'll just count that. Just shot that over there. Hopefully I didn't hit beam with it. Oh, that wasn't smart. Okay. So this is the trick. If you have a breadboard, use it. Use it in order to actually put your positive pins onto your device. You can do things like solder one pin on one end of it, and then basically bend the rest of them into the right place. That works if you don't have a breadboard. But if you have one, by all means, just use the breadboard. So, all right, let's move this back. Let's actually focus in on this. Okay. So, this is the trick. It's not that hard. If you have a good soldering iron, which I realize that's a big if, it should glob up right into a nice little pin right on your end. And there's lots of different tips too. I find that a tip like this is what will do 80% of what you're trying to do. You can get away with it. And obviously, if you're soldering like way bigger stuff, way bigger gauge wires to like batteries and stuff and things like that, then you need like a hand welder. Not a hand welder. That's wrong. A hand soldering gun. And just pure wattage output. Everything with soldering is heat. It's all about heat and where the flux is. The liquid metal wants to go where the heat is, and the heat is distributed properly by the flux. And the flux also allows I think it's like basically like adhesion. It's like surface tension. It allows it to be pulled through the lattice. At least that's how it behaves to me. So actually, just to be really, here we'll do this. We'll do a little experiment. This is kind of like best case scenario as far as soldering. Like this is super easy. Everything is just sitting here, especially with the breadboard. It's like not hard to do. Let me zoom even more. This is pretty cool. Look at that. Holy crap. All right. So that wasn't great. Probably put a little bit too much heat into there. But the idea is, you do not need to use pressure. If you're using pressure, then you're doing it wrong. Everything is about actually making contact with the liquid metal. So if you want to make something hot, you need to not contact it with the tip. You need to contact it with the liquid metal that is melted onto the tip. So that was a pin with the flux on it. Now let's try it without it. So I'm gonna glob up a little bit bigger of a pool here so that I can actually do what I was saying. And you can see, like, as we're going here, we're building up a gunk. Just one go of that, and the flux, when if you get it too hot, which you're inevitably going to, it will build up a black gunk. So then, if that happens, you scrape it off. Scrape it off. Oop. Gets nice and shiny again. Here, it'll be even more shiny if I do this. And then put it. And also, I have my iron set at 480 Fahrenheit right now. So generally, when it's kind of counterintuitive, but when you're doing PCB soldering and repair work, you actually want as much heat as possible, because you need to be able to make the solder go where you need it, and then as soon as that's the case, take the heat off. Like, you don't want to be sapping a lot of heat into the piece itself, only where you want the heat to go. So these pins and these contacts are nice. So this is easy. I mean, I'm not even going to bother fluxing all of these pins. But like, if you're having trouble, then the rule is to just go for it and to use as much flux as you need, really. Like, using too much flux isn't going to make a problem, other than being a messy cleanup, because depending on the kind, the kind that I have is like a tacky flux. It's kind of nasty. It smells weird, but. And I don't know how well you can see it, but you kind of want like a liquid cone, you know. You want it to actually seep in. You don't want a blob. You don't want like anything like a bubble. You don't want a bubble of solder. You want it to seem like it's actually like spread out and made contact with all of both the pin and the contact itself on the component. Put this battery out of the way here. Put a little flux on the tip. Something that you might want to be careful of with this. I've broken a couple of them. This has been like 2 years now that I've been working with this particular board, but it's real easy, because of how small this board is, to hold the soldering iron tip and touch this faceplate here, which all of the brains are inside of this, and this is basically a heat sink, but it's not enough of a heat sink that it can take the soldering iron for very long. So, and depending on where you touch it, if you accidentally touch that when you're trying to solder these pins, then you can break the board. And it won't happen immediately, but it'll happen pretty quick. So something that applies for both soldering and welding. The key and one of the most important things that people will tend to forget, especially if they get frustrated, is get comfortable. Like, do not try to use your iron and the solder itself like in a scenario where you're not in a good position to do so. Like, I turned the entire workpiece here so that I can actually just hit it from the same angle, and it's closer to me, rather than reaching over and trying to. Wow, you just got a good look at my skin there. Rather than trying to reach over and do some precarious position. Something that people will say, and probably also applies here, when you're welding, if you can avoid it, you want to stay away from welding the same spot for longer than you need to. You want to allow the heat to dissipate. So, like, me going one after the other, you know, right to left or left to right, maybe isn't the best idea. Like, maybe it's, and granted, it's like, as long as I'm doing this correctly, it really shouldn't be a problem. But just, you know, common sense wise, it's not a bad idea to alternate, go back and forth, you know, let the heat spread evenly rather than building up in one part of the board. Something else that makes life a lot easier is if you actually like stick your board down to the table, or just some other way hold your workpiece. I mean, a lot of times on a breadboard it's pretty easy for me. I'm not used to it. It's fine for it to move around a little bit on me, but you got to use helping hands. So that's another big thing. It's like, if you're, depending on what you're trying to do, if you're trying to solder wires together and they're small, and or it's just you really should have that as a bare minimum. And you don't need a lot. Like, you only need like one or two clamps usually, and that's what I've got here. I've got 3 on this, and I use one to just hold my solder wire. All right, now I'm going to visually inspect this and make sure that it looks okay. Yeah, it looks good. So, let me show you. None of them are bridging between each other. And like I said, they're like liquid cones. Looks like everything's nice and evenly coated. They're all about the same size, and they're not big and globbed up. So that looks good. So now we can just pull this out with perf. Okay. Now, how this works. This is a lot simpler than you think. You can see on the sides here, positive, negative. You can do whatever you want. I mean, all that it really means is that the positives are all connected and the negatives are all connected. You can put the positive on the negative, and that's up to you to figure out. I mean, you probably don't fight convention on purpose, but and then this is the way that you can actually, like, you could write out your schematic kind of like even in a table if you wanted. So connection B4, you know, is over here. And the thing is that all of row 1, these are all connected. Okay. So you get 5 connections to run on the same rail, if that's how you want to think about it. So the way that you generally do it is you use your positive and negative to be your power supply, and then you jump power over to different collections here, and that's your idea. So how this will work, we'll bridge this. Here at the bottom, so that I can plug the wire in at the back here, and still have access to all of these pins. So basically, I'll look at the schematic and see, okay, this is in a general. So they're called GPIO pins, the important ones that you need to use and program, and that stands for General Purpose Input Output. So I'll take one of these GPIO pins, hook a wire into the rail that's connected to it, and then jump that over somewhere else where it's more manageable, and then I can, you know, do whatever I want. I can hook that pin over to another component. So I don't know. Will these go in here? Sorry. Oh, beauteous. Okay, cool. So this is a potentiometer. Got some hair on it. This is a 20K. I think that I should be able to program it however I want. This is a 5K, but it has stuff soldered to it. So depending on how you're trying to use these things, it's like the prongs may or may not be helpful. So I just soldered directly onto them here. Not really fun to do. Different metals will take the solder better than others. So yeah, not my favorite thing to do. We're gonna try to. Is this my 5? Oh yeah, this is another 5K. We're gonna use this, and the reason why it doesn't matter very much is because I'm gonna use this potentiometer as basically my speed control. I'm gonna check my chat quick, make sure no one tried to message me at all. No? Okay, good. Makes my life easier. So the way that we actually need to do this is that we can't just plug this in this way. Because if we did it this way, and these are all generally speaking, like a standard distance apart. Pins are a standard distance. But if we put it this way, then this is pointless because every single pin here on the potentiometer is connected to itself because it's all on the same rail. So the only way that this is like valid or useful to do is if we put this, plug it in, make sure you don't bend it. Plug it into the breadboard down here at the end like that. So now we're bridging on 3 different rails, and the way that a pot works, we call them pots, is that it's basically a wiper in here, and as the wiper moves back and forth, really around a contact, it changes. It's shifting the resistance between the middle pin and each outer pin. Okay, so this is a 5K potentiometer. When it's in one direction, then its resistance is 5,000 on between the middle and one of the pins, okay, and 0 on the other one. So, and then as you go, it linearly changes, to the opposite, to the inverse. So we're only going to need to use one. We're only going to need to use the middle pin and one of the outer pins in order to pull this off. Honestly, the fun part sometimes is getting the 12-volt wires to actually work with the fan here. But let's just as a sanity check, put 12 volts on this fan and make sure that it's actually working right. These fans are fun. I gotta find the right wire here. Okay, so what I'm gonna do is I'm gonna hook this together. You want to spiral it around the bigger wire. And then wire nut it up. And now be careful because this is now live, even though this is the negative side. And the thing is with DC, and I mean, unless you're dealing with high voltage, as long as you don't bridge the gap, so to speak, and just be ginger, be careful. You won't actually do anything. And also, moisture is a big factor. So like your skin is actually generally pretty dry depending on the time of year, and it will actually protect you from a lot of things. But not everything. And like a high enough voltage will be able to jump to you, and that's no bueno. So we're gonna plug this into here. So this is my negative. That's going into my black here on the end. Like I said, they usually put the ground on the outside just because it's the most likely to ground out, I guess, probably. That would be my reasoning. I lost my, I'm not sure where my smaller wire cutters are, my strippers. Which is really not good because I keep, this is not ideal here. Alright, let's see if this will work. Even that doesn't work. Okay, those kind of work for me. This one's short now, though. Crud. Okay, so same deal. Okay, now, when I connect this, this should turn on. Oh, there it goes. Pretty cool, huh? Yeah. So there you go. Now, the idea, how we do it nowadays, is we supply a constant 12 volts to the device, and then we send what's called a PWM signal, a pulse width modulation. So we change basically the length of the pulse that we send to the fan itself, and the pulse is in a logic voltage, so it's not at 12 volts. It's not like we're sending it an actual power signal, which is how they used to do it. They used to actually modulate the amount of power that they were sending to the fan, and that would increase the speed up or down. But now we just, like I said, you still apply it with 12 volts, and then it has an intelligent board on it that then changes the speed up or down more efficiently, basically. And what you do is you take, if you notice, there's 4 pins on here. You take the tachometer, so the speed of the fan, and then you correlate that to whatever pulse width you want or need. So even though you send it depending on the load, so like depending on what you have this hooked up to, 50% PWM, so sending the pulse width 50% of the time will correlate to a different fan speed based on the load on the fan, unless you do in programming, you say, okay, we're going to compensate for that, and like no matter what it's hooked up to, we're going to modulate 50% PWM to mean this particular fan speed. And you figure that out and send the right signal to the fan via the feedback that you get from the tachometer signal. One thing that's not great is that, and this is always the case with these things, is this blue pin is pulling out of here. Let me zoom in. So they're great and they're not. Honestly, I'm thinking about this. I probably switched this around. I could look into an old file and try to figure this out, but the truth is that the tachometer isn't gonna hurt the controller, and then sending a signal on the tachometer to the fan is not gonna hurt it either. So as long as it's the right voltage signal. So we're just gonna send the signal on each of them and see which one actually makes it work. Now, yeah, you can see these are all boogered up. Because I had pried the. Ooh, that doesn't look good. Yeah, well, if you push it back up in here, see these little tabs hold the metal female pin in place, and when you screw with them, when you pull them out, when you pull the tab up so that you can pull the female pin header out, it just they just don't last forever. They wear out. Okay, now if we want to actually modulate this fan, we need to use this guy. And here's the thing. So like, if I wanted, actually, yeah, I don't really need to do that right now. Let me think about this. It is a little bit sketch to hook your computer up to your microcontroller when you're also trying to control something with a 12 volt supply. Simply because if something goes wrong in the controller, if you burn something out the wrong way, then you can actually get a backfeed. So it's really they're designed so that it would prevent it for the most part, but it's still kind of sketchy. I should probably buy like an external hub that is like a surge protector basically, and so like if something bad occurs like on the breadboard, then it won't actually propagate back to the computer. But what I'm going to do instead is we're going to program it separately, and then we're going to power it with this little guy. So this is a how do I, yeah. So I mean this has a range on it. I'm not sure exactly what the range is. Is this a boost or a buck? I think this is a buck converter. So a boost will boost the voltage up, and a buck converter takes it down. And this is actually another potentiometer. So this is another form factor that a potentiometer can come in, and this is kind of doing the same thing that I was explaining, and except rather than sending the PWM signal that you're modulating with this potentiometer to a fan, you're sending it to whatever. So like you can modulate voltage also via PWM. So if you have 12 volts and you send it a 50% PWM, that will actually correlate to another lower voltage, and then you can smooth that voltage, rather than having peaks and troughs with a capacitor. So you put a capacitor after that PWM voltage signal, and you can then smooth out that lower voltage that you're trying to output. So this is I don't know, kind of weird. These are really tiny little pads here for this, but I guess it is what it is. Well, we're just gonna go with it. So I got a bunch of wire here. Let me grab it. I'm gonna use blue. I'm gonna use blue as my 5-volt wire color because we're already using red for 12 volt. And if you're using two different voltages, I generally will use two different colors for positive. I got a bird's nest here. Should have done a better job of not making this a mess. This silicone wire is great. It's really just nice and flexy. I haven't really found many disadvantages to it yet. I think it might be a little less durable, but it's way nicer to work with. I don't know. Okay, now you don't have to overthink this. What I generally do on something like this is I just, basically loop it through, and then glob up a nice little cap of solder there, and that'll be good enough. I didn't even use flux there. This is kind of like child's play on like these types of solders. So you can see that filled in really nice. That's a really strong connection. That's as strong as the wire is going to be. So then what I'll do for this. So, oh yeah, something else that's pretty much absolutely necessary when you're doing this kind of work is a pair of micro snips like this. Dink. Gone. Nice, and that's flush. They're also called flush cutters for that reason. Okay. So now we got outputs, just like that. Cool. These were probably excessively long, these wires that I made for this, because now I'm going to want to actually, and this is what gets super annoying, is, speaking of which, I should probably find some heat shrink. Is soldering these jumper wires onto normal wires is so annoying. Alright, these leads are really long. And also, keep in mind, I'm keeping in the back of my mind the fact that I have a hot 12 volt hanging dangling here, and the 12 volt negative here. Okay, as long as these don't touch, we're fine. Okay, so this can like dangle here; it's not going to hurt me or anything. So, depending on the size of the wire, you want to leave different amounts of, strip different amounts of wire to accomplish what you want. I don't really know if there's a right or wrong way to do this. I've just kind of done this. This is what I do. I take them, I cross them at about halfway of the length of both of them, and then I just twist them around each other. And the thing is before you do that, you also want to make sure that you get a heat shrink on there. So, and depending on the size of the heat shrink, if you're using bigger heat shrink, then you can just slip it right around the jumper head. Heat shrink is one thing I forgot about. Okay. Well, for simplicity's sake, we're just going to use some electrical tape, since we're also just prototyping right now. Don't really know the right or wrong way to use this either. I've seen people say flags, so you can just basically just hook them on there like little flags. So here's what we're going to do. We're still going to solder it, so we got a good connection and nothing pulls apart. But since we're not using heat shrink, we don't have to worry about doing that, like getting it on the wire first. So make it look like this. it's irritating because it's like you go too far and then you can't see anything. Yeah, so get it looking like that. Then throw it in your helping hands. And I mean, I'm just going to hook it like this. I only need one helping hand right now because it's hooked together. So people will say that you need to tin your tip, and that's absolutely true. And not only for your soldering iron, but also for the tips of the wire. So you like, in this scenario, I didn't do that just because it's a super fine and stranded wire. But if it's not, then you really, depending on what you're trying to do, especially if you're just trying to do wire to wire like this, you want to tin each of them so that they can actually create a molten contact to one another. Okay, so before I solder the other one, we're just going to tape it up. So just like this. That's actually a lot of tape. I'm going to cut this in tape in half. Okay, same deal. Kind of just get a glob on the iron. See that I used a little bit too much here, so there's still some glob here, and there's a glob on the actual wire itself. Kind of like spread it out, like paint it. It's not really the best thing. You want to just use the right amount of solder for the job, ideally. But if you get a little extra, you can just kind of smush it out a bit. Okay. God, it's like behind me. This phone camera thing is pretty cool. This is awesome. Okay. So now we have this. Let's look up the schematic of the actual Arduino chow so that we can then hook the jumper cables into the right spot. Is this what I want to do? Yeah. Okay. Yeah, so this is the right. I want to find one where it actually shows which ones are analog and digital, though, because not all these are analog outputs. Where's the right thing? Wait, actually I think it's I think it's this thing here. It's this. Maybe not. What I was doing was online. You can get either a data sheet or something that includes like aspects of the data sheet. This one has a tutorial somewhere, which is kind of just as nice. Yeah, this is it. That's it. Okay, here we go. There we go. Okay. So you can see here that are these all? I don't think that's right. Yeah, only these ones are actually analog outputs. I don't understand what this QT means. I really don't. Because if we look at my if we look at my schematic here, yeah, A45. Only, well, 1, 2, 3, 4, 6. Did I save this? This looks like I might have lost some progress on this. Why do I have open analogs here? That's not right. Q-Touch. Not right now, Bean. I'm sorry, but I'm working on something here, and I'm handling hot stuff. Okay. Well, either way, I'm almost positive that this is an analog output that I can use. So we're gonna use, and this is, it gets confusing because they'll use 0 as a number. Let's figure out how to get this so it's actually in your field of view here. We gotta get power into this buck converter. So that means this here. How should we do this? Now we're gonna take a red wire. Solder this to the inside, so you can see just directionally we're going out to 5 volts. At least that's what we want to do. Same thing. Spitter. Honestly, whenever you're doing any type of stuff like this, you should probably be wearing safety glasses, especially with the micro snips, they can shoot stuff right in your eyes if you're trying to clip pins and stuff. I'm not really doing anything that's that scary right now. If I do, I will put goggles on. Should have checked the length of this. Oh. Good. Okay. Now, basically, the plan is we're just going to combine this. We're going to take the jumper wires out of the wire nut and put in this. So, strip it back. Make sure. All right, now I gotta be cognizant here. This is gonna be live as soon as I plug that in. As soon as I hook up the wire nut, I mean. So let's get this on the actual correct breadboard pins here. So if we look at our diagram, we can see that 5 volts is the furthest to the front left. Actually, okay, so what? Is that really necessary? Yeah, not really. So what I was thinking I should do is make a 5-volt rail, like an actual power supply on the side, and then jump that over to power the actual controller. But since we don't really have to power anything else with 5 volts, we're just gonna not do that. So the next one is ground. So we're gonna plug this in here, as so. So that one's already connected, and now as soon as I hook up this positive 12 volt, this controller should turn on. Oh, wait. Okay. So it's good that I didn't do that just yet, because I haven't actually checked that this is going to be outputting the correct voltage. So what we're going to do before we actually hook it directly to the controller is we're going to confirm that. So okay, you're just going to have to take my word for it that we're probing the right wires. So right now we've got 0, okay, and that's to be expected because I haven't actually plugged this in yet. Now I'm pretty sure there's a light on here, so we should get some indication that we're actually doing something. I don't see a light. So let's hope that, make sure I did everything right. Looks right. Okay, let's see if we've got an output voltage. 0.5 volts. Okay. I have a broken tip here. That's not good. I think it should still work to turn this pot though. Now I turned it a little bit in one direction. We're going to see if it went up or down. Hasn't done anything. Okay. So, what is going wrong? It could be broken. It could be as simple as that. These aren't really super high quality components. Alright, so we have the voltage going in, but just nothing coming out. So I'm going to try to finagle this and basically twist this pot as I have it probed. This isn't good. It's probably broken. Yeah, that's not right. It could just be it could be I'm almost positive this would take a 12 volt. Interesting. I think it's busted. Okay, so disconnect our positive. Let me go see if I have another one of these. I'm pretty sure I do. Actually, let me see. I'll use this. This has terminals too. What a luxury. Ooh, almost lost the camera. I'm gonna make sure this isn't a boost. Let's just see what happens. Let's just see what it does. I mean, if it displays more, then it just is what it is. Let's not get too confused here. All right, let's get this out of here, actually, since we're not going to be using this anymore. Oh, duh. So I hooked to the out. Dum-dum. I grab some more. I only got one here. Do I need more than that? Not really. Wire not up to positive output. One thing that you should keep in mind about terminals is that just always back them all the way up, because you can easily get stuck underneath them. These are awfully big wires for this terminal too. Yeah, so these wires are really big for these tiny terminals, so it's not really, they're oversized for what we're trying to do. So I'll actually cut some of the strands off. Trust me, it's safer than trying to leave them all on there and then the conductor like sticking out. This is really just a trial and error process. You want to twist the strands up nice so that they actually stay together when you try to push it into the terminal. See, like, since I snipped that down, it goes in there a lot better without too much of it sticking out. Okay. Got that. Now here's the problem. These are using the same color wires now, but it's not too bad. I've dealt with a lot worse. This is sketch. So make sure you don't have any stragglers sticking out of your Alright. Now I have both of the outputs wire knotted up. As soon as I stick this into this terminal, we should get lights on this. And when you snip off the strands, make sure that they don't fall directly into your piece. And periodically, because you know those little strands of copper wire can short something out. Make sure it isn't too long so that you can actually get it all the way into the screw terminal. Little spark. This might be a boost. Nice. Okay. Now, as you can see, well, maybe you can see if I actually point it the right way. I don't know how well you can actually read this. Let me turn out the lights. So this is a boost converter. I forgot what I had here. So if I had a universal power supply, my life would be so much easier. It'll be coming here in the next month or two. I promise you. So right now, we've got 12 going in, 11.35 whatever, and we have 15 coming out. Now if I, oops, trying to. Now if I loosen up this pot, loosening it up, it's going down. I'm literally like right in the way. Okay. Loosening it makes it go down. And this is nice enough that it has a display on it. I'm not sure how high it goes. It depends on its input, how much it can boost it, and the current. Okay. Well, that's not going to work for what we want to do, though. So. And you want to be careful when you do shit like this. So now that I cut this way down like this, that's not enough of a conductor to actually get the wire nut on there, probably. I mean, we can try it. It'll actually grab the shield, like the actual like it'll actually grab the what is it even called? I mean, what is this plastic, I wonder, on wires? Probably some kind of PET. But it will, the spring, the conical spring in the wire nuts will grab that too, but it's a little less reliable in my experience. Okay, that's good enough though. Kind of like running out of steam here on this particular project. I'm probably gonna come back to this. I think what I want to do right now, and what can be pretty easy, is the fume hood, the extractor. So something that I managed to do, I think we're going to move on now, is I got some dimensions working to an extent on this. I made sure it was like especially sealed though, because for what I was trying to do, but with some of this mounting putty. But I got the right threading, like so that I can thread these HEPA filters for gas masks directly onto a 3D printed part. So what I'm imagining is just a little fume extractor. So basically just this part, like just this aspect of it, and then it like on a little stand, like right, and then I can put it somewhere and just have a switch or whatever. I don't know. I'm a little tired. It's been an hour and a half. I think that was a pretty good live lab. Showing like basic soldering techniques is like pretty important, I think. And let me expand myself a little bit. General soldering techniques are like crucial to electronics work and just repair work as well. So hopefully I learned something as far as that goes. And I might actually, at first I was thinking I was going to do the podcast like maybe more than once a week, but I think I'm actually going to do this more than once a week. So I think I'll do this twice a week. I'll probably do a Tuesday and a Thursday, or maybe a Monday and a Thursday. But anyway, thanks for tuning in, and